Hello, my name is Laura Alford. This is the first lecture in our series on hydrostatics, and it is on the geometry of ships. So ships, like all specialized things, they have their own set of terminology that might be unfamiliar to you if you have not run into it before. So that's what this lecture is sort of aimed at familiarizing you with. So the first thing and the major thing is the hull. The hull is the big outside part of the ship that you see if you go see a ship down at a dock. The front part is called the bow, and the back part is called the stern. Left is port, and right is starboard. If you are standing in the middle of the hull and you're walking towards the bow, you're said to be going forward. And if you are in the middle of the ship and you are heading back towards the stern, you're said to be walking aft. Now you can see from this is just an example hull here, and this little kind of there's a bulbous bow. That's that little part that sticks out. This is very complicated, right? It's very curvy, it's higher in some parts than others, it's narrower in some parts than others. This is pretty complicated. And it gets kind of tricky talking about the hull if you've got a problem and you're trying to explain to somebody where exactly it is or what's going on. So we've got some reference planes that we can use to help ourselves with. So there's a big vertical one that goes down the center line of the ship. It is very creatively called the centerline plane. There's a horizontal plane called the waterline plane and a transverse plane that's called the midship plane. You'll notice this little symbol here with the circle with the two arcs bisecting it, sort of. That's the symbol for the midship. That's the middle of the ship. So if you see that symbol, we'll run into that before, but that's all it means. It's just put at the center of the ship. Right. As an example, take water lines. If you were to take the waterline plane, make a bunch of different copies of it, and run it from the keel line, which is the bottom of the hull here, all the way up to the top deck, you get these blue lines here. And from the side and from the front, they look straight, right? Because they are horizontal slices of the hull. But if you look at this from the top or from the side, sort of from this oblique view, then you get a sense for the curvature of the ship as it changes from the keel all the way up to the top decks. And so now we say, okay, here are some lines. We can start to see more of how the hull is changing, what its real shape is here. Similarly, if you take the midship section plane and you take a bunch of copies of it and put a bunch forward and a bunch aft, you get what are called stations. The stations here from the side and from the top look straight, which is good. That's what you want. And then from the front or the back or from this oblique view, now you get these sectional curves here. And you can see that they illustrate how the hull is changing as you go from the bow to the stern. Here, you see down below here, right, if you were to plot all those red lines on top of each other, it would get kind of busy. It'd be tough to see which ones are going where. So generally we put the stations that are forward of midships on the right-hand side and stations that are aft of midships on the left-hand side. This way you can see how things are changing easier. And most ships, almost all of them, have a port-starboard symmetry. So you're still retaining all of the information here. Okay. So finally, if you take the centerline plane and you take a bunch of copies and you send them port and starboard, you get what are called buttock lines. So again, from the top and from the front or back view, you get straight lines. But then if you look at it from the side or from this oblique view, now you start to get these contours as you go from port to starboard or left to right. So now you can see how is the ship's hull changing from side to side. And you can look at these lines, and they're sort of like the lines of pressure on a weather map, right? The closer the lines are on a weather map, then the higher the wind is going to be. Similarly, the closer the lines are on these slices here, the closer the lines are, the more curvature there is, and the farther apart they are, the less curvature there is. You can take all of these lines, put them all together in something called a lines drawing. The profile view at the top shows the buttock lines, the plan view shows the water lines, and then the body plan shows the stations. Again, remembering that the body plan shows the stations that are forward of midships on the right and the stations that are aft of midships on the left. Now, in general, a lines drawing is going to have a whole bunch more information than just what I've shown here. They'll have station numbers and dimensions, scales, labels, all this stuff. This is just an illustrative example here, just to show you where these lines are coming from. Okay, so there are several different lengths that we end up using when we talk about ships. There's an overall length, which is very important when you're looking at how much dock length do I need to actually bring my ship up to a dock, right? You got to make sure you have room enough for the entire ship. But when you're looking at this ship and how it's going to behave in the water, you often don't really care about the part that's above the water because it's not going to have much of an influence. You're looking at the water, the part of the hull that's underneath the water. And so we talk about this length on the waterline, which is how much of the ship is actually corresponding to being inside in the water. There are a couple of perpendiculars. These are vertical lines. The forward perpendicular at the bow often is placed at where the bow of the ship intersects the water line. So we put a vertical line there. There's the aft perpendicular, can be placed at a similar location where it's where the stern of the ship intersects the water, but it could also be placed at where the rudder goes or where the propeller shaft might come out of the ship. It just sort of depends. So you have to look and see how it's defined. But then you have the length between perpendiculars. It's just the length that's between wherever those two perpendiculars are defined. All right, just to compare a little bit, here is an example of the length overall, here shown in gray as a horizontal slice. And if you do the same thing, but now you do it on the waterline, you get the length on the waterline. So you can see how different these are. And this would have an effect when you're doing calculations later on. So you can see, if you're trying to get more accurate information on how the ship is going to behave in the water, this length on the waterline will give you a better representation, better representative length in your calculations. Right. Beam is the width of the ship. It is almost always just the maximum beam, which is almost always at midships. So just example here of what that means in terms of some of the slices of the hull that we've already seen. There are two major vertical measures here of the ship. One is depth, and that's the overall height of the entire hull. But when you go back and you're looking at buoyancy, stability, sea keeping, you're concerned more about how much of the hull is actually underwater, and that's draft. So you can see here. They're both measured from the keel line. Again, the keel line is the very bottom of the ship. And then the difference between the two is called freeboard. And freeboard becomes very important when we do stability later on in a different lecture. All right, so now we've got some of these numbers. We can start to use them to compare ships. So some commonly used ratios are length to beam, length to depth, beam to draft, and beam to depth. So again, just know these, remember what they are. They're not very inventively named. There's L over B, that kind of stuff. Okay. So we've got a basic sense of the geometry and stuff. There's some characteristics now that we use to compare ships and also to do calculations later on. So I want to start with the waterplane here. So here's what I mean by the waterplane. You take a horizontal slice of the hull. This is the part that's in gray. Now, if you do the same thing, but you do it right at the waterline where the hull intersects the surface of the water, you get the area of the waterplane, this A sub W here, that's shown in red. You can then calculate a waterplane coefficient, which is just the area of the waterplane divided by the length times the beam. So you can see here in the illustrations how much of the waterplane is actually being taken up by the ship as compared to how much could it possibly be taken up based on the length and the beam. Here the length is going to be the length on the waterline, and the waterplane coefficient describes how full or fine the waterplane is. For a ship that is relatively fast, like a destroyer, this is going to be lower, like this 0.67. For a very large tanker, which is very much concerned with how much cargo can you carry, this is going to be higher. So like this 0.92 means that 92% of the possible waterplane, that greenish rectangle, would be taken up by a large tanker. Not nearly the case with a destroyer, which would look more like kind of what this is here. Okay. Again, there's a center of flotation with the waterplane. Now, what it means is, picture in your head a ship, right, and you're loading some stuff on it, and as you load it on the bow or the stern, it's going to tip a bit. It tips about this center of flotation. The center of flotation corresponds with the trim axis, again, which is what the ship is going to rotate about. The center of flotation is a point, right? So it's got 3 different coordinates to it. There's a longitudinal, transverse, and a vertical. The longitudinal is called the LCF, for longitudinal center of flotation. It is almost always measured from midships, but it can be measured from the aft perpendicular or from the forward perpendicular. So just check to see if you're working on a ship, check to see what it's been defined as. Okay. With the waterplane, it has a couple of different moments of inertia. The first one is the longitudinal moment of inertia. This is the moment of the area about the trim axis here. This inertia is almost always going to be calculated for you by a hydrostatics program on the computer. So you just run the calculations and it gives you this number. So you just need to know what it is and where you use it. Similarly, there is a transverse moment of inertia. It's, again, the second moment of area, but this time it's about the center line. Again, it's calculated for you by a hydrostatics program, so just know what it is and where to use it. And don't get the two mixed up because they are very different numbers. Okay. Moving on to the underwater volume. Definition here. Because we use V later on for velocity, we had to come up with something different to talk about volume, and so this is what we use this triangle for. You may have seen it with as a gradient symbol in math class, but here we use it as the volume of water that's displaced by the ship. So it's that part shown in red. So you can see that it's not the entire volume of the hull; it's just the part that is underneath the water. Okay. The center of this volume is the center of buoyancy. It is the point through which the total buoyancy acts. So again, it's a point, so it has 3 dimensions. There are 2 that we're primarily concerned about because, again, going back to the fact that ships generally have a port and starboard symmetry, the horizontal, the transverse coordinate for the center of buoyancy is almost always on the center line, so don't worry about that one too much. Instead, we're looking at the longitudinal center of buoyancy, which is the LCB. This is, again, similarly to the LCF, longitudinal center of flotation. It's generally measured from midships, but it can be measured from the aft perpendicular or from the forward perpendicular, so just check to see. The vertical center of buoyancy is always measured from the keel, hence its designation here KB for keel to center of buoyancy B here. All right, station areas. If you were to take a transverse slice of the hull, right, and you look at that, okay, the area that's below the design water line is going to be the station area, and it's shown in red here. So again, it's not going to be the total area of the hull, it's just what corresponds to being underneath the water. Similarly, if you do this at midships, then you get the midship station area. And the same thing, it's just the area below the design water line at midships. Now, if you do that all along for all of your stations, you can plot the sectional areas on the sectional area curve, and you can see that it has less area at the bow, and then it increases as you get towards midships, and then it comes back down, and you have less area at the stern. Because the area would then be related to the volume, this kind of gives you an idea of where your buoyancy is going to be coming from, which we'll talk about later. So the bulk of buoyancy is going to be coming around midships, not so much at bow and stern. Your hydrostatics program will calculate this for you. You can do it for a lot of different drafts because there'll be a bunch of different drafts that you need to be concerned with. Then you mark one as the design water line. You do some that are greater than that, some that are lower than that, and then you plot them all together. And again, it gives you a sense of how is your ship going to be changing as you have these different drafts for different loading conditions. Okay. Block coefficient is a very important one in terms of for how you can compare different ships. Even if they're the same kind of ship, you can compare them using the block coefficient. So it describes the overall fullness of the hull. And you can see here, so it's the total volume that it could possibly take up based on length times beam times draft. But then you compare that to how much it actually takes up, right? Which is the volume in red here. So here's how you calculate CB here. Again, the length is usually the length on the water line. For a destroyer that is primarily concerned with speed and performance, it's going to have a finer hull, so it will have a lower block coefficient. But for a very large tanker, which is trying to haul a bunch of cargo, it's going to have a much fuller hull, which means that its block coefficient will be higher. So again, it is one number, right, that can compare hulls that are very complicated and may look very differently. You can boil it down to a number that you can sort of wrap your head around. Similarly, you have a prismatic coefficient. Because the midship sections of ships are so full, sometimes they can overwhelm the differences between the bows and sterns of different ships. So here's one way that you can more directly compare how the bows and the sterns of different ships are. So in this case, you take the area of the midship, you extrude it out fore and aft with times the length of the ship, and then you take the actual underwater volume and divide it by that new volume here. Again, so the destroyer here, now we've got a little bit different value, it's 0.57. The very large tanker is still kind of 0.8 because it is so dominated by volume. You don't get much of a change as compared to the block coefficient, but the destroyer, you do get a change. So midship section coefficient, again, you can sort of compare how full is a ship right at the midship, right? For a destroyer, or actually start with the large tanker, 0.95, it means 95% of that green rectangle will be taken up by a ship if you're talking about a tanker. A destroyer, which is going to be more concerned with, again, speed and performance, it's going to have a bit more streamlined shape, kind of more probably similar to what I've got here. A note that the block coefficient is actually equal to the prismatic coefficient times the midship section coefficient. So if you know any two of those, you can calculate the third. All right, so some notes to remember. all of this stuff that we've talked about here will change with draft. So going back to that sectional area curve where you calculate it for different drafts, you do the same thing for all of this stuff. The pictures that are shown here are just instructional. Your ship will look differently. And the dimensions listed here are the molded dimensions. It means like from the very outside of the ship to the other very outside of the ship. They don't include the plate thickness from when you're actually building the ship. So it's just a note. Generally, all the stuff that we've talked about here, the dimensions and the characteristics will be calculated for you on the computer, because computers, they're really good at calculating things. But you have to go back and make sure that makes sense. Like going back and just doing basic checks, like checking to see that the block coefficient, the prismatic coefficient, and the midship section coefficient all agree. Right? You need to go back and do that. So this is the quick introduction to ship geometry here. I hope that it was useful. We'll continue on with hydrostatics. We'll get into some stability and damage stability and lots of good stuff, but this should hopefully be a good start. So thank you very much for watching, and we'll see you next time.